Physical datum reference frame construction. A concept. Hello, my name is Tom Vanderloop, and today we're going to look at the datum reference frame concept. And we're going to take a look at it from a few different perspectives and get a feel for what the datum reference frame is. And the datum reference frame is basically everywhere, and we use it in engineering for a lot of different applications. The datum reference frame is merely a framework that has a plane surface in this direction, a plane surface in this direction, and then another plane surface back in here that more or less ties the geometry of any part together into a usable description. We more or less say that the datum reference frame exists in a world that might look something like what we have here. Alright, the datum reference frame, also abbreviated DRF, is everywhere, and it's common to engineering, it's common to manufacturing, and it's also common to quality. When we think of the datum reference frame, we think of three mutually perpendicular planes. We possibly have a plane that goes in this direction, and that plane might be defined as a horizontal type plane, or a plane that we define as the x-plane. Then we have a y-plane that might go vertically up and down, and then that y-plane we could say establishes a frontal type of geometry, can go from the front to the back along a type of an axis. And then we have another third one, and with the third one we define the x, we define the y, and we define the z-axis. Now you can see basically that we have three axes that we view, and we can look at four quadrants. If we define one quadrant and we define a third quadrant, in the first and third quadrants we could possibly come up with a application of the datum reference frame, and the application of the datum reference frame that we might come up with or we might work with could be called a glass box. And in America, when we look at the object, we look at the observer, we look at the glass planes of glass, the mutually perpendicular planes, and we look at the object on the inside. Well, this is set up in the third quadrant, and when we have it set up in the third quadrant, as you can see here, we put the glass box here in the third quadrant. We've got the observer, we've got the glass box, and we've got the object inside of the quadrant, and we call that third angle projection. Now, third angle projection means that you've got the object projected in a relationship of the third quadrant. And it kind of looks something like what we have here. There is the observer, there is the glass planes, and the object goes on the inside. So we're using this three-plane concept everywhere. We use it in orthographic projection, and of course this orthographic projection concept is the result of a number of years of evolution. It was probably first used 400 or 500 years ago in Europe, and we took the concept and we carried it into our drawings today. And in America we use everything basically in the third quadrant. So here you can see the third quadrant, how it works. Here you can kind of get a feel for how it might be set up, and so that's where third angle projection comes from. In the other countries, they put everything here in this first quadrant, and when you have that first quadrant, we call that first angle projection, because we have the observer, we have the object, and then we take the object and we put it onto the glass plane. And then you see what we have as a result here is the object is projected from the object to the plane, and we call that the first angle projection. So in America, we use this third quadrant, In the rest of the world, they use this first quadrant, and we come up with two different planes of projection, or two different ways to look at an object. In simple terms, the Americans use the projection here, and they use what we call third angle projection. And with third angle projection, we get an arrangement of the views where we've got a front view, a top view, a bottom view, a right side, a left side, and a rear. And it becomes fairly easy for an individual to view an object. But as soon as we get into first angle projection, things change slightly because we are in the first quadrant, and what happens is the bottom view will move to the top, and then the right side here will move to the left side here. And so these four views, the top, the bottom, the right side, the left side, all change or all move, and what we get is we get an arrangement in the foreign countries. This is known as United States projection, third angle projection, but in the foreign countries, the bottom view becomes the top view becomes the bottom, the right side becomes the left side, and the left side becomes the right. And when we rotate the part and make it look like this, where this becomes the left side, this becomes the right side, this becomes the bottom, this becomes the top, these four, when they exchange, this is known as foreign projection, or another name is first angle projection. Now, 3/4 of the world uses this first angle projection, but the United States and Canada pretty much use third angle projection. Now, third angle projection is definitely the more logical, and it's the one that we work with the most often. Okay, so that's one use or one application of the datum reference frame construction, is with the use of first angle and third angle projection. And of course, in the United States, when we use that, we use third angle projection. When we look at the foreign countries, France, Germany, Japan, they would basically all use first angle projection with their datum reference frame construction. Okay, this datum reference frame is not only in the visualization of an object, like we might use in geometry to define our CAD drawings, but we also use this datum reference frame when we work in our tooling and in our manufacturing. What I'm going to do is I'm going to set a part here on the table, and we're going to locate this feature here with our part. And this feature, we're going to say, rests on a single plane, and this line right here, this line represents a secondary datum, and then when we slide this over right here, this line would represent a tertiary datum. Now, with this particular part, if you look at this, we'd want to locate this in the x direction from here to here, and we'd want to locate this in the y direction from here to here, and so we'd actually build this part from this 0 point. Now, this point on the datum reference frame, that's called 0 point. So the 0 point is located off of the x and off of the y, and where that intersection is, we call that 0. So there's the 0 point. We come over from the 0 point a distance, that's our x direction. We come up this distance, that's a y direction, and by locating x and y, we use a datum reference frame to identify what a part might look like if a part were square or rectangular. Now, those parts could be plastic parts, and they could be parts where when we mold them from the x and y datum, and we set them up accordingly. Now, when we get to round parts are a little bit different. Round parts are built from the inside out. Square parts, steel parts that are located off of x and y directions, we say they're built from the outside in. we come from the outside datum, which might be a plane surface datum, and then we come in a distance of x, a distance of y, and we locate the part accordingly. Well, with the plane surface datum, that's not a problem, but as soon as we get to parts that are round, now we build everything off of what we call a zero velocity point. And when we build a part off the zero velocity point, we get an arrangement that looks something like this. We take the part, the x-axis of the datum reference frame construction, the x-axis is in this direction, the y-axis is in this direction, and we call this physical datum reference frame construction concept the three-dimensional datum reference frame, and the zero velocity point is considered a line axis, a three-dimensional line axis. It's located down here at the bottom of the feature. We call this point right there, we call that the 0 point where x and y cross, and as we come up on the part, and three-dimensionally you can see as we come up, we have defined what we call an axis line. Some people on a CAD drawing might call that axis line. Well, that's the center line. But you want to remember this, that line or that axis, that zero velocity point, that in theory really exists because of that circle that you call out. And that circle that you call out is this inside bore or this inside diameter. It's this outside feature out here, and everything had its origin or originated from this line. So with our datum reference frame concepts, we have three geometric constructions. We have a 0 point, and that's our origin. We have an axis here from the origin outward, which we call that axis a line of axis. And then, of course, we have the flat surface, which represents the plane. And with round parts, when we construct the round parts are built off of a zero velocity point. So as this part rotates, we define that zero velocity point accordingly. Now you can see this quite easily when we put the part on our table here. And you can see that we can set the alignment. We can see the 0 point, and there's the 0 point. We can see that there's a point at the bottom which calls 0. We come up this distance called our z distance, and from 0 to z we create a line. And then we have our horizontal axis, we have our vertical axis, and from that we can create what we call the physical datum reference frame construction. And the physical datum reference frame construction captures the part and defines the geometry, and all of this is basically the result of how we control our parts. So in conclusion, you want to understand that the physical datum reference frame construction is the theoretical perfect horizontal or x, the vertical or y, and then our z is our depth. If we look at it from a more physical application, you can take your hand, you can establish your x direction, you can establish your y direction, and your thumb would represent the z direction. So if I were to take the x and lay this down for an inspection purpose, the x is the horizontal, the y is the vertical, and then the z is my thumb. So I got x, I got y, and I've got z. So everyone should be able to physically identify the x, y, and z, which stands for the three-dimensional datum reference frame concept. We use it everywhere. On the CAD system, we'll use it and we'll define it as our grid, and our grid will be set accordingly. And our grid will either be a two-dimensional grid or it'll be a three-dimensional grid if we work with wireframes. So we've got both of those when we work with CAD. When we get into manufacturing, the fixtures that we work with define the x direction, the y direction, and the z direction. And then when we get into inspection of parts and we go to the coordinate measuring machine, we'll take the parts, we'll put them on the coordinate measuring machine, and we'll read the x direction will read the y direction, which will be on the flat table of the coordinate measuring machine, and then the z direction will go up from that flat table accordingly. So whether it's in design, whether it's in manufacturing, or whether it's in quality, the datum reference frame is everywhere. The last thing, orthographic projection with the 6 normal surfaces. They define the horizontal plane for the top and for the bottom. They define the profile plane for the right side and for the left side, and they define the front and back of the part. As we see here, there's our front of the part, there's the back of the part. That would be our z direction accordingly. And so you can set the datum reference frame to use in many applications. In CAD, in design, we use it for visualization. We also use it for measurement. And when we look in manufacturing, the physical datum reference frame construction is everywhere, and we use that physical datum reference frame to define the x direction, the y direction, and then of course the z direction, which goes in and out.